Good day, learners. Welcome to our physical sciences lesson. My name is Ameni Mkize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, our focus today is on electrostatics. You should know that the field is strong when the lines are close together, right? So when the lines, if you see that the lines are close together, or if you see that the electric field lines are close together, so you must know that what the electric field it's strong. The strength there it's what is very strong, and then it is weak when the lines are far apart, right? So that is how we can represent what the strength of the electric field, right? So if the lines are close together, right, you should know that the electric field strength is stronger, and then if the lines are far apart, the electric field strength is what it's weaker. And then the number of field lines is proportional to the magnitude of what of the charge. Although we are not going to focus more on that, but here we are just representing what the electric field using the electric field lines around a charged what object, or around what a charged sphere, or around an electric charge. Okay, right. So then how do we determine what the direction of the field lines? Right, so now we have talked about how we should draw those electric field lines, right? But now to determine the direction of the electric field, right? How do we determine that? So the direction of the electric field represents the direction of the force a positive test charge will experience if placed in the electric field. So in other words, the direction of the electric field at a point in space is the same direction in which the positive test charge will move placed at that point. So we'll understand that better when we draw the electric field the electric field lines. And remember what you did in grade 10, right? When it comes to the charges, you are aware that like charges they repel, but the unlike charges they attract. Okay, so we are going to use that. Okay, then let's start with a positive charge, right? So this is a positive charge, so we want to represent what the electric field around this positive charge. Okay, so we will start by drawing what those electric field lines, but please make sure that you follow the properties of electric field lines when you draw those field lines. Okay, so how do we draw them? Please, when you draw them, make sure that the lines they do not intersect, or the line they do not touch or cross each other, right? And make sure that when you draw these lines should be drawn perpendicular to the surface of the charge. Okay, so you can see here the lines are drawn perpendicular to the surface of the charge, right? Then this is how we have to draw the electric field lines around that charged sphere. Okay, so now how do we identify the direction of the electric field lines? Okay, so these are your field lines around this positive charge. All right, so you can see they are drawn perpendicular to to the surface of the charge. So they're drawn perpendicular to the surface of the charge. Okay, and please make sure that the lines, when you draw them, right, they should start from the surface of that charge, not from the atmosphere. They should start from the surface of that charge. So please make sure. All right, so we don't expect something like this and you say these are electric field lines. No, the lines should start from the surface, of that sphere. And please make sure that you draw them perpendicular, so that always drawn perpendicular to to the surface of the electric charge. Okay, then now how do we determine the direction of the electric field, right? Okay, so the direction of the electric field, we use a positive test charge. Okay, so I can place this is the electric field, so I can place the positive test charge anywhere here, right? Okay. Now, ask yourself a question, right? Remember, you have a knowledge of what happens to like charges, what happens to unlike charges, right? So unlike charges, they attract, like charges, they what? They repel. Ne? So now you have this positive what? Test charge. You want to determine what is the direction of the electric field, right? So to determine the direction of the electric field, you use a positive test charge, right? So this is a positive charge, right? Then you place it anywhere, you know, where you have these electric field lines, all right, where you have the electric field, which, because remember, the electric field is around this charge, okay? So now what is going to happen to this positive test charge, right? If it's placed in this position, right? So this sphere is positive, right? And the test charge is also what? Positive, right? So now, between like charges, what happens? There is force of what? Of repulsion. So how do we determine the direction of the electric field? Use a positive test charge. Will this positive test charge move towards or away from this electric charge, right? Obvious, both charges here, they are what? They are positive. So this test charge, what will determine the direction of this electric field is the direction actually of the force, all right, exerted by what? By this electric charge to this positive test charge, okay? So this positive test charge obviously will move away. Why am I saying it will move away? It will move away because like charge is what? They repel, okay? So this what positive test charge will move what? Will move away. So as it moves away, obviously already now we have the direction of what? Of the electric field, okay? Let me go back. How do we determine the direction of the electric field? The direction of the electric field represents the direction of the force. Represents what? The direction of the force a positive test charge will experience if placed in the electric field. So I've placed this positive test charge in the electric field, okay? So now, will this positive test charge move towards or away from this electric charge? Obviously, it will move away. So that what direction of the force actually is the direction of the electric field. I'm not sure if it's making sense. So how do we determine the direction of what? Of the electric field? We use a positive test charge, right? So place a positive test charge in the electric field. This is the electric field, right? So then get the direction of the force. Will this positive test charge move towards or away? It will move away. So that away direction actually is also the direction of what? Of the electric field. So it will move away, move away, move away. So this will be the direction of what? Of the electric field around this positive what? Electric charge. I hope it's making sense. Even if I can place it here, it doesn't matter. Or as long as it's along the electric field, right? So ask yourself a question. What will happen to this positive test charge? Obviously, it should move away, right? Because like charges, they repel. So it moves away. So this actually is the direction of the force exerted by this electric charge to this positive test charge, okay? And this direction of the force exerted by this electric charge to this positive test charge actually gives us what? The direction of the electric field. I hope it's making sense. So this is the electric field pattern around, or the electric field around what? A positive what? A positive electric charge. Okay? Now let's move to a negative one, right? So this is a negative what? Electric charge, right? Then we start by drawing the electric field lines. Make sure that the lines, they do not cross or touch, or they do not intersect, right? If you do that, you are not following the properties of the electric field lines, right? So already I'm having those lines drawn perpendicular starting from the surface of what? Of the electric charge, okay? from the surface of the electric what? Of the electric charge. Then now I want to get the direction of the what? Of the electric field. Okay? So how am I going to get the direction of the electric field? To get the direction of the electric field, I need a positive test charge. So place the positive test charge on the electric field, right? There is my positive test charge. Ne? So then find the direction of the force exerted by what? By this negative electric charge to this positive test charge, right? Unlike charges, they what? They attract. So what will happen to the positive test charge? Obviously, this positive test charge will move what? Will move towards this negative electric charge, okay? Because unlike charges, they what? They attract. So the force exerted by this negative charge to this positive charge, right? Obviously, it's going to be what? It's going to be towards each other. There is force of what here? Of attraction. So to get the direction of the electric field, I don't want us to memorize, right? Because I know in most cases we'll say lines or they run from positive to negative. Actually, it's not like that. How do we get the direction? How do we get the direction of what? Of the electric field? We use a positive test charge. Take a positive test charge, place it in that electric field. Then get the direction of the force exerted by this electric charge, this negative charge to this positive charge, right? Obviously, there will be force of what? Of attraction. So this positive charge will move towards. So this is the direction of the force exerted by this negative electric charge to this positive charge. Okay, so you can see it's towards. Then already we have what now? The direction of the electric field around what? This negative electric what? Electric charge. Right. So this is the electric field pattern around what? What is this? Around a negative, a single negative charge. Okay. I hope we are still together. Please make sure that when you draw the lines, they start from the surface and they're always drawn perpendicular to the surface of the charge, right? And how do we get the direction of the electric field? Use a positive test charge. So if you place a positive test charge next to a positive electric charge, there will be force of repulsion. So if it's force of repulsion, so it means that what the direction will be away, right? But now when it comes to a positive charge and when it comes to a negative charge and a positive test charge, what will happen to that positive test charge? It will move towards. Then that will be the direction of what? Of the electric field around the negative charge. I hope it's making sense. Ne? Then here we have negative. You can see negative charge. Then electric field. The electric field lines. These are the electric field lines. Please make sure that you draw them correctly. How they do not intersect or cross or touch each other. Draw them perpendicular to the surface of the charge, right? And how do we get the direction? Use a positive test charge. Will this positive test charge move towards or away to this negative charge? Obviously, it will move what? It will move towards. Hence, the direction is like this, right? Then this is a positive what? A sphere. Then to get the direction of the electric field, use the positive test charge. Obviously, this positive test charge will move what? Will move away. Hence, the direction you can see it's what? It's away. So these are electric field patterns around a single negative charge and a single positive what? Positive charge. Okay. Moyana, will the added test charge always be positive? Yes. The test charge is always positive. Test charge is always positive, right? So to get the direction of the electric field, we always use a positive test charge, right? Unless if you are told, especially when it comes to questions, sometimes they will say this charge, it's what? It is negative. But if it's not mentioned, you should know that the point charge, right, is always what? positive. Ne? Even when it comes to getting the direction or of the electric field around a charged object or a charged sphere, we always use a positive test charge. So the charge is always positive, unless if you are told otherwise that this charge is not positive, it is negative. But if it's not mentioned, always it should be a positive. You see when it comes to questions. Ne? Right, then this is the electric field pattern between two positive charges. So you have a positive charge. Ne? But now can you see now you have how many charges? There are two. So it's two like charges. And what we know from grade 10 is that like charges, they repel. So you can see how this one is drawn. Ne? It's unlike when we have a single positive charge or a single negative charge. So these two, right? Between like charges, there is force of repulsion. So when you draw, you must show repulsion. As we can see here, so this is repulsion. Ne? This is how you need to draw them. There will be force of repulsion. Force of repulsion. Throughout, force of repulsion. Even this side, force of repulsion. Is force of repulsion. So it's repulsion throughout. Okay? And how do we find the direction of the electric field lines? We use the positive test charge. So if the positive test charge is placed next to this positive electric charge, obviously there will be force of of repulsion. So it will move away, right? So hence here you can see the direction is away from this charge, away. Even here, because it's still positive, away. And please make sure that the lines that do not cross or touch, they are always drawn perpendicular to the surface, right? Then let's check this one. So here it's between positive and negative charge. So positive, negative charge, right? So remember, between unlike charges, there's force of attraction. So when you draw, you must show that there's attraction between these two charges, right? So attraction. This is how we do it. Ne? Attraction. And please make sure that, especially when it comes to this one, please make sure that the lines, they do not cross or touch each other. So you can see attraction. Ne? So they shouldn't touch. Okay? All right. And now, how do we find the direction of the electric field? Use a positive test charge. So if I can place it here, right? My focus is this positive charge for now, right? So obvious, this charge, positive test charge will move away from this positive electric charge. Ne? So it will move away, but moving towards to this negative charge. Ne? So that is why the line, the direction is from what? Is from positive to negative. Because this positive test charge will move away from this positive electric charge and also move towards this negative electric charge. Hence the lines will, the direction will be from positive to negative. Okay, so I hope it's making sense. So that is between positive and negative charge. So electric field, learners, they lose marks here. One, the reason why they lose marks, you will find that when they draw, right? You can see here there's force of attraction, right? So you have a positive charge and a negative charge. Obvious, there must be force of what? Of attraction. And this attraction should be throughout. Ne? In most cases, learners will give us something that we've never seen before, right? You have a positive charge, negative charge. And then we'll find that here, okay, attraction, attraction, attraction. And we are happy, right? Lines obvious from positive to what? To negative. But after some time, you find a learner drawing something like this. Something like this. We don't accept something like this, learners. Why? Remember here there's force of attraction. If it's force of attraction, it should be attraction throughout. You can't have attraction and repulsion at the same time. Because if now you draw something like this, it's like initially there was attraction, but at the end there is what? There is repulsion. Do you have something like that? No. So if it's attraction, you can even see here. You can even see here that there is attraction throughout. Attraction throughout. Unlike charges, they what? They attract. So we don't accept something like this. Please. Let's not draw something like this. There's attraction, and at the same time, there's what? There's repulsion. It's like we are confused. We shouldn't. You shouldn't be confused, learners, right? So when it comes to patterns, it's where you have to get the marks. Make sure that when you draw those lines, they do not touch, they do not cross each other. Draw them perpendicular. Make sure the issue of direction. Use a positive test charge. If it's a single charge, place a positive charge in the electric field. Obviously, that positive charge will move away. Then we'll get the direction away from that positive electric charge. If it's a single negative charge, draw the lines, right? Make sure that the lines, they do not cross touch, right? And again, they are drawn perpendicular. They start from the sphere, or they start from that electric charge. And again, how do we get the direction? The direction, use a positive test charge. Positive test charge, is it going to move towards or away? It obviously is going to move towards, because it's negative versus positive. Unlike charges, they attract, right? If it's two positive charges, for example, like it or not, there will be force of repulsion, and it should be repulsion throughout. Repulsion throughout. Ne? It shouldn't be repulsion and at the same time it's attraction. Maybe you draw something like this. There's repulsion, and then again you have something like this. It can be. If it's repulsion, it should be repulsion throughout. If it's attraction, it should be attraction throughout. Okay? Then we can even make an example with negative charges, two negative charges. Again, here there's force of what, learners? Repulsion. Repulsion. Make sure that lines, they do not cross or touch each other. Repulsion, right? Repulsion, repulsion. Okay? Repulsion. So it should be repulsion throughout. Repulsion throughout. Okay? Repulsion throughout. Then, how do we get the direction of what? Of the electric field? Use a positive test charge. So for both electric charges here, right? There will be force of what? Of attraction. So it's towards. The positive test charge will move towards this negative electric charge. Towards. And make sure that the lines, they do not cross or touch. Like charges, repel. And when you draw your electric field pattern, make sure that they repel like this. Unlike charges, they attract. This is attraction, right? And make sure that there's attraction throughout. A single charge, this is what we're expecting. A single positive charge here, a single negative charge here. Clear? This is how we have to draw the electric field pattern. What is the difference between the field lines for different types of fields? For different types of fields, I'm not sure, because yes, we have different types of fields. Ne? For example, we have gravitational field, we have magnetic field, we have what? Electric field. Maybe I can make an example with electric field and magnetic field. The way we represent magnetic field and electric field, we represent it the same way. We use the electric field, we use the field lines, okay? And make sure again, when you draw the field lines, right, they do not cross touch or each other. But for electric field, how do we find the direction of the field lines, right, or the electric field? You use a positive test charge. But for when it comes to a magnetic field, right, how do you determine the direction of the magnetic field, right? The lines, they always run from north to what? To south. Okay. So what is the difference between the field lines for different types of what? Of lines? Yeah, there's no difference. We represent it the same way. Like, for example, your magnetic field and your electric field, we represent it what? We use the field lines. We use the same properties of what? Of field lines. It's just that there is a difference. We have, if we talk of magnetic field, that is the region in space where the magnetic object will experience what? A force. But electric field, right? It's the region in space where a charged object, or where an electric charge will experience a force. That is the difference. But when you represent the field lines, we represent them the same way. Same properties are being used, all right? But you should know that there's a difference. Magnetic field, electric field, those are two different concepts, although we represent the field lines the same way. Okay, so I think I've tried to answer your question. Okay, now let's look at electric field at a point. So I think we are fine now with with the electric field pattern. Please, learners, I know some, I don't want to comment more on that, but okay, I think we have seen how we draw the electric field lines, right? Please, let's do the right thing. If it's attraction, it should be attraction throughout. If it's repulsion, it should be repulsion throughout. And another thing that you need to be careful about, all right? Please do not draw extra lines. What am I trying to say there? Okay? Although we won't penalize you. But you see this line, it continues like this to this one, right? Even this one, it continues like this, right? Even this one, you see, it continues like this. So if, for example, let's say we have something like this, positive, negative. So it's the continuation, right? Okay. Then you do something like this. Okay. Right? So, okay, fine. This one continues. Even this one continues. But look at this one. It doesn't continue, right? What is the meaning of this? It means that your charges here, they are not identical. So check your, what is this? Your exam guideline. Here we deal with what? We deal with what? Identical what? Charges. So if you do something like this, actually we should penalize you. So please make sure that we don't draw something like this. Although you'll get a mark for the shape, a mark for the direction and all that, but you shouldn't actually get a mark for the whole thing, right? Why? Because what you are dealing with here is, remember, according to our ATP, we should deal with what? Identical what? Charges. So if they're like this, it's like it's saying to us, this charge is greater than this one. Okay? So, and it shouldn't be like that. So when you draw lines, don't just draw. So make sure that even if I don't see that line there, but I can complete it the way I've done it here. So this is how actually we also need to draw, our electric field field patterns. Now let's look at the electric field at a point. Let's not confuse electric field with electric field at what? At a point. What is electric field at a point? Electric field at a point is the electrostatic force experienced per unit positive charge placed at what? At that point. That is the electrostatic force experienced per unit positive charge placed at what? At that point. So that is the electrostatic force experienced per unit positive charge placed at what? At that point. Okay? Then what is the electric field? Is the region in space where a charged object, or where an electric charge will experience what? Will experience what? A force. But this one, it's a force experienced. The force experienced per unit positive charge placed at what? At that point. So let's not confuse the two. Then in symbols, E is given by F over Q. All right? Then E, remember, is the electric field. The symbol for electric field at a point, it's E. So don't think that E is for energy, right? So E, it's not energy. It's what? It's electric field at a point. All right? And then F is the electrostatic force, which is measured in newtons. And then Q is the charge, which is measured in what? In coulombs. So E is equals to F over what? Over Q. And remember, F is in newtons. This one is in coulombs. Then E, which is the electric field at a point, is newtons per what? per coulomb. So that is the SI unit for electric field at what? At the point. It is the electrostatic force experienced per unit positive charge placed at what? At that point. So E is the electric field at the point measured in newtons per coulomb, and then F is the electrostatic force measured in what? In newtons, and then Q is the charge measured in what? In coulombs, right? So, and again, what you need to know is that electric field at a point is a vector. It is what? A vector. It has both magnitude and what? And direction. So electric field at a point is a vector. It has both magnitude and what? And direction. And remember, F is also a vector, right? So what is happening here is that E and F, they're always in the same what? Same direction. So if the direction of the force is to the left, even the direction of electric field at a point is going to be to the left. So E and F, they're always in the same what? Direction. So E always takes the direction of F. Remember, we are saying electric field is the electrostatic force experienced per what? Per unit positive charge placed at what? At that point, right? So E and F, they're always in the same what? Direction. So if the direction of F is east, it means that even the direction of E is going to be what? East, right? So in symbols, right? There's something, which is this, right? E is given by F over Q, right? And remember, E and F in this case, they're directly what? Proportional. E and F, they're directly what? Proportional at constant what? At constant Q. So here, I was showing actually the relationship between E and F using a graph, right? So if F increases, E also increases with what? With the same factor, okay? As the magnitude of the force increases, electric field at a point also what? Also increases. So which means that electric field at a point depends on what? It depends on what? On F, which when F increases, E also what? Also increases. Okay, so this graph shows the direct proportionality between E and what? And F. Okay, then if they can ask you, because you can get a graph like this, okay, if they can ask you about the dependent variable, you must be able to tell them that this is electric field, or you can say electric field at a point measured in newtons per coulomb, and then the independent variable will be the electrostatic force, or a force which is measured in what? In newtons. Okay, then again, they can even ask you about the physical quantity represented by the gradient of this graph, right? So what are you supposed to do? Go straight to your data sheet, check an equation where you have E and what? And F. That equation is E equals to F over what? Over Q. Then according to this graph, what is your Y? Your Y, which is the vertical axis, is E. What is your X, which is your, what is this? Which is your independent what? Variable. So in this case is what? Is F, right? So what are you supposed to do here? You have to arrange this equation in a form of what? Y equals to mx plus c, because this is a straight line. And equation of a straight line is y equals to mx plus what? Plus c, when it comes to your mathematics, right? So you have to manipulate this equation in a form of y equals to mx plus c, making sure that your y is what? Is E, and then your x is what? Is F, right? So let's try to do that. I'm having E equals to what? F over Q, which is going to be F times what? Or maybe let me just do this, which is going to be what? 1, right? Right, which is going to be what? 1 over Q times what? Times F. So 1 over Q times F is the same as F over Q. So here I'm having y equals to mx. My x here is F, correct? And then my y here is what? Is E, which is also what? Correct. Which means that the gradient of this graph represents 1 over what? Over Q. So can you see that you can use this graph? You can use this graph to calculate the charge, right? You can use this graph to calculate what? The charge. How? You start by calculating what? The gradient.
So when you calculate the gradient, let's not forget, you need how many points? 2 points. Let's say this point is 0 is to 0. Maybe this one is 5 is to what? Is to 5. I'm just giving you an example. So then you calculate what? Your gradient. Your gradient here will be changed in E, which is E final minus E initial, over change in F, which is F final minus F what? F initial. What is your E final? Your E final, it's going to be what here? This point is 5 is to what? Is to 5. So it will be 5. That is your E final. Then your E initial is what? Is 0. And then your final F is 5 minus what? Minus 0. Then your answer here will be 1. That will be your gradient. So your gradient is 1. But remember, gradient represents the inverse of the charge. Gradient represents the inverse of what? Of the charge. So what is your gradient? It's 1. Then equals to 1 over what? Over Q. So like it, your Q here will be what? Will be 1 what? Would be 1 coulomb. So you can use this graph because that is how they ask questions. Sometimes they just even run away from those statements. They will give you the graph. Then if you are unable to interpret the graph, then you are in trouble. So this is how we need to interpret it. So here what I was doing, I was showing the relationship between E and F, right? E and F that are directly proportional at constant Q, right? So as F increases, the electric field at a point also increases. So I have shown that relationship using a graph. So it's going to be a straight line since there's a direct proportionality between E and F, right? So now, how do I interpret the graph? Dependent variable, independent variable. Another secret is the area and the gradient. So in this case, there's no physical quantity represented by the area. So there is a physical quantity represented by what? By the gradient. So the gradient in this case represents what? The inverse of the charge. So if it represents the inverse of the charge, then I can get the charge, okay, using this graph. So this is how actually you need to interpret your graphs, okay. Then another thing, still on this, right? The relationship now between E and Q. E and Q, they are inversely proportional in this case, right? But E and what? And the inverse of Q, right? E and Q inversely proportional, which means that if this is constant and I'm increasing this, right? I'm increasing this Q, your E is going to decrease. But now, what about E and the inverse of charge? Obviously, the relationship will be directly what? Proportional. Since E and Q is inversely what? Proportional. So you can even prove this with values, right? Check if you increase Q, what will happen to E? You will see your E is going to decrease. That is E and Q according to this what equation. But now, maybe let me try to do that, maybe with only two values. You have E equals to F over Q. The only thing that you want to change here, it's your Q. Your F remains the same. So let's say you decide that your F will be just 1 Newton. But what are you changing is Q. Your initial Q, let's say, is 1. Your Q2, let's say, is what? It's 2. Your Q3, maybe let's say it's what? Is 4. So what are you increasing here? It's your Q, right? So then I will have E1 as 1 over, remember my F, it's a constant in this case, so I've decided to use 1 there, all right? So it's going to be 1 over. What is my Q1? My Q1 is 1. Then here my E will be what? Will be 1 Newton per what? Per coulomb. Let's check my E2. My E2 will be 1 over what? Over 2, which is going to be 0.5 what? Newtons per what? Per coulomb, right? Then my E3 is 1 over what? Over 4, which is going to be what? Maybe 0.25 what? Newtons per what? Per coulomb. So can you see that when I have E and Q, this is the relationship, okay? This is going to be the relationship. So as Q increases, what happens to E? E decreases. You can see my E is increasing. 1, 2, 4. That is, my Q is increasing. 1, 2, 4. But look at my E. What is happening to my E, which is the electric field at a point? My E, it's what? It's decreasing. 1 to 0.5 to 0.25. I hope you understand that. Okay. So as I increase Q, what happens to E? E decreases. So I'm having E and Q there. The relationship is inversely proportional. So as Q increases, my E decreases, right? But now I'm looking at what now? I'm looking at E and the inverse of Q, right? So now what am I having here? I'm having E, right? And the inverse of what? Of Q. So actually I'm having something like this. 1 over Q times what? Times F. So my F here is what? Is constant. Okay? So constant, but what is changing is 1 over Q. 1 over Q, which is 1 over Q1. Let's say it's 1. Right? Okay? I hope you are following. So what am I changing here is the inverse of Q. Then what is 1 over Q2? Let's say it's 2. Right? Okay? So I'm looking at my E1 now. What is changing is 1 over Q. What is 1 over Q1? It's 1. Then my E, like it or not, will be what? Will be 1 Newton per coulomb. Right? E2. What is 1 over Q? It's what now? Is 2. So it's going to be 2, which is equals to what? 2 newtons per watt per coulomb. So can you see that as my 1 over Q increases? Because remember what is changing here is 1 over Q. It's no longer Q, but it's 1 over Q. So I'm having 1 over Q times F according to this equation. So what am I changing is 1 over Q. But remember my F is constant. It's 1, for example, right? So I'm multiplying 1 times 1, which is going to be 1. 2 times 1, which is going to be what? To be 2. So can you see that as I increase 1 over Q, what happens to E? E also increases by the same factor. Look at it, my 1 over Q, it's 1. What is your E1? It's also 1. Look at my 1 over Q2, is 2. Look at my E2, is also what? Is 2. So as I increase 1 over Q, your E also increases with the same factor, right? Which means that when what this 2 increases by the same factor, it means that they're directly proportional, okay? So hence I'm having this graph. So between E and 1 over Q, the relationship is directly proportional. It should make sense because between E and Q is inversely proportional. If between E and Q is inversely proportional, it means that between E and the inverse of Q, the relationship will be what? Will be directly proportional, right? So if they can ask you, they can give you a graph like this and you must be able to answer questions based on this graph. What is the dependent variable? It's your E, which is your what? Your electric field at a point, right? What is your independent variable? Along the horizontal axis, you have an independent variable. Your independent variable, Lenas, is not Q. What I see here is 1 over Q. So it's the inverse of Q, which is my what? My independent what? Variable. Then another secret, you already know, is there a physical quantity represented by the gradient, by the area here? So this is what here? A triangle. You can even prove that on your own. Ne? So this is what? A triangle. What is the area of a triangle, right? Area of a triangle is half a base times what? Times height. Ne? So area will be half base times what? Times height. Remember, it's area under the graph. I did explain that. If I say under, I'm not saying under the horizontal axis. No, I'm not saying under the horizontal axis. Under the graph. The line that you have drawn, the line that shows the direct proportionality, they are saying under that line. With other words, they are talking about what? Which area? This area between the horizontal axis and this line that you have drawn that shows the direct proportionality between what? Between your E and the inverse of Q. All right. So that is why I'm saying to you, I'm having a triangle there. Area under the graph. Which graph? They are not talking about the axis. No, the graph, the line that we have drawn, which represent that relationship between E and what? And 1 over Q. So it's half base times height. So it's half. What is your base? Your base is 1 over Q, and then your height is what? It's E. All right. So I'm having what? A half. 1 over Q is per coulomb, which is 1 over C. I'm using the units here. And then what is E? Is Newton per what? Per coulomb. So if I add these two, or if I multiply these two, what am I going to have if I multiply these two? So I just want to check if, is there a physical quantity represented by the area under this graph? Ne? Is there a physical quantity represented by the area under this graph? Ne? Under this graph. So what am I having here? I'm having half times what? C to the power negative 2 times n. So it's n actually per coulomb squared. Do we have a physical quantity with this SI unit? We don't have a physical quantity with this SI unit. So actually, there is no physical quantity represented by the area under this graph. Why am I saying that? We don't have a physical quantity with this type of SI unit. I hope it's making sense, right? So these are some of the things that you need to do, because you are not a prophet. You need to prove whether, so I hope it's understandable here. You must know your story here. If you don't know, then you can't even tell whether is there physical quantity with this SI unit. So you must know the SI unit for each and every physical quantity, so that you'll be able to tell which physical quantity represented by the area or which physical quantity represented by the gradient. Okay, now let's move to gradient. Because there's no physical quantity represented by the area, then now we need to move to gradient. Right? We are moving to gradient. Right, so with the gradient, what are you supposed to do? Check what you have all along your horizontal axis and your vertical axis. You have E and Q, or E and 1 over Q. Check again. Go straight to your data sheet. Check the equation where you have your E and your Q. That equation is E equals to what? F over what? Over Q, right? Then arrange this equation in the form of y equals to mx plus c, because this is a straight line. Equation of a straight line is y equals to mx. What is your y in this case is E. What is your x in this case is 1 over q. That is your x. Then rearrange this equation in the form of y equals to mx plus c, making sure that your y is E, your x is 1 over q, right? So it's E equals to what here? F times what? 1 over q. Y equals to mx. So you can see my x here is what? It's 1 over q. My y is what? Is E, correct? Correct. Which means that the gradient here represents what? The force. So you can calculate the force using the gradient in this case. So if the gradient is 5, it means that the force experienced here is what? Is 5 what? Is 5 newtons. So these are some of the things that you need to know under electrostatics, the interpretation of graphs. You must understand what is going on. We don't want a situation where you are given a graph and you don't even know where to start. It shouldn't be like that. You must be able to give us the what? The dependent variable, independent variable, the physical quantities, either represented by the area, by the gradient. Give us the conclusion based on the graph. So what could be the conclusion, for example, in this case? As the inverse of charge, which is 1 over q, increases, E also what? Also increases. Or you can say E, which is the electric field. Electric field at a point is directly proportional to what? To 1 over q, or is directly proportional to what? To the inverse of charge. So you must be able to give us those things. Those are simple things, ne? Right? And the one that is a bit, challenging is the one of area and the gradient. But I've shown you several times how we should get that. Okay, just a reminder again of what we did the previous 2 weeks. Make sure that you are able to convert, because when it comes to these equations, your Q should be in coulombs, right? So as I hope you still remember how to convert from what? From millicoulombs to coulombs. You multiply by 10 to the power negative 3. From micro coulombs to coulombs, multiply by 10 to the power negative 6. From nanocoulombs to coulombs. So here it should be nano, not P. So it's nanocoulombs to coulombs. You multiply by 10 to the power negative 9. There is also pico. Let's not forget pico coulombs, which is PC. Here it should be NC, not PC. And then 2 coulombs. All right? So how to convert that? You multiply that by 10 to the power negative 12 for what? 12 coulombs. So let's not forget that. Right? Very, very important. When you use equation E equals to KQ over R squared, your Q should be in coulombs. So if you are given it in nano, you must be able to convert. In pico, you must be able to convert. In micro, you must be able to what? To convert. Same with the distance, you must be able to convert distance to what? To meters. If it's given in millimeters, you need to convert it to what? To meters. How? By multiplying by 10 to the power negative 3, or you divide by 1000. From centimeters to meters, you multiply by 10 to the power negative what? Negative 2, or divide by 100. Ne? So here is either you divide by 1000, here you divide by 100, and then here you multiply by 1000 from kilometers to meters. Right? So these are some of the things that you need to know for you to be able to get all the marks when it comes to calculations in this topic. All right? Then, very, very important, the issue of the constants. The constants, please do not memorize them. There's no need. There's a lot that you have to memorize. So there's no need to memorize K, the value of K, the value of E, the value of M. There's no need. You are given those constants, right? So your G, actually our focus is this one. So there's no need. And again, you know what I like about this, right? What I like about this, very, very important. If you're using the equation, which is this one, your K, remember they're saying the units is N square meters per coulomb, if I'm not mistaken. Yes. So which means that your force should be in newtons. Your R should be in meters, which is your distance. Your Q, which is the charge, should be in what? In coulombs. So it's clear. Even here, your K, right? Your Q should be in coulombs. Your R should be in what? In meters. So this is very, very important. This is very, very important, learners. All right. So you can see you have all the equations there that we have to use under electrostatics, calculating the electrostatic force, calculating the electric field given the distance, calculating the electric field not given the distance, given a force and the charge. And then this equation, it's where now we have to calculate the number of electrons transferred, and then where Q is the charge transferred. And remember the charge transferred, if we talk of charge transferred, you did this in grade 10, charge transferred from one sphere to the next. So it's Q, change in Q, which is what? Q final minus what? Q initial. Unless if you are asked to calculate the number of excess electrons, you are just given a negative sphere, maybe they're saying it's 2 coulombs, and they want you to calculate the number of electrons in excess. Obvious, this Q will be these 2 coulombs, right? But if charges are brought into contact and separated, this Q will be the charge transfer, will be the charge transferred, right? How to calculate the charge transferred is QF minus QI. I'm not sure if learners, you understand that part. This equation, very, very important. If you are given this charge, they want you to calculate the number of electrons in excess, because there's excess electrons here, is -2. The equation will be N equals to Q over E. Ne? What is Q? Is 2, or -2, is still fine. Ne? What is E? Is -1.6 times 10 to the power negative what? 19. Then you'll be able to get the number of electrons in excess, right? But let's say now we have this sphere, -2 coulombs, and is brought into contact with -3 coulombs, right? What are you supposed to do here? If you want to calculate the number of electrons transferred, you will need the charge transferred. How do you get the charge? I'm just reminding you of what you did in grade 10. How do you get a charge transferred? First thing that you need to do is to calculate the new charge after contact. How to calculate the new charge is Q equals to Q1 plus Q2 over what? Over 2. And this equation, you can see grade 11s. This equation is not there on the data sheet. For grade 10s it's there, but for grade 11s it's there. So it means that you should know it by heart. Right? So Q1, Q2, negative 2 plus negative 3 over 2. What am I having here? It is going to be what? Negative, negative, which is going to be negative 5 divided by 2, which is negative 2.5 what? Coulombs. That is the charge on each sphere after contact. Okay? So this is the new charge or final charge. Okay? Then charge transferred is final charge, which is negative 2.5 minus the initial charge. You can take either negative 2 or negative 3. So I can take negative what? Negative 2. Then that will be the charge what? Transferred. Then when I calculate the number of electrons, it will be N equals to Q over E, which is change in Q over what? Over E. I hope what I'm doing here is making sense. So don't confuse. When it comes to this equation, you can calculate the number of electrons in excess. For example, you're giving a negative sphere, right? You can calculate the number of electrons in excess in that sphere, all right? Then how to calculate the number of electrons transferred from one sphere to the next, right? First thing that you need to do is to calculate what? The new charge after contact. Then after calculating the new charge after contact, calculate the charge transferred, which is the final charge minus initial charge. What is your final charge? Is the charge on each sphere after contact. What is the initial charge? Is either this negative 2 or that negative 3. But at the end, you will get the same magnitude. Okay? Then from there, you'll be able to calculate what? The number of electrons transferred from one sphere to the next. Right? So now let's look at the multiple choice questions. The electric field between two oppositely charged spheres is E. That is the electric field. Ne? If the distance between the spheres is doubled, the electric field becomes, so it's the issue of proportionality here. So the equation is E equals to K Q over R squared. Okay? So what are they changing here? The distance is doubled. Okay? The distance is what? Is doubled. So if the distance is doubled, what would be the new electric field? What will be the new electric what? Field. So this is the old electric field, KQ over R squared. The new electric field, let's calculate the new electric field. Okay, so the new electric field, the distance is now doubled. So I'm having new electric field, which is KQ over what? The distance is doubled. So it's twice R, but it's all what? All squared. Okay, which is going to be what? KQ over 4R squared, which is the same as 1 over 4 KQ over R squared. But remember, this KQ over R squared is what? Is old E, which is the same as 1 over 4 what? 1 over 4 E. So here is just the issue of proportionality. So these are some of the things that you need to understand. So the correct answer here will be what? Will be 1 over 4 what? 1 over 4 E. So choose the correct equation and then use that equation to get what we are looking for. Right. Then the SI unit of the electric field at a point is, this one is straightforward. E, electric field, you can even use the definition, right? Electric field, it's or electric field at a point is the electrostatic force experienced by a positive a test charge placed at that point. So it's F equals to E equals to F over what? Over Q. F is in newtons and then Q is in coulombs, which is the same as what? Newtons per watt per coulomb. So the correct answer there is simple, this one. The correct answer is what? It's B. All right. Then the third one, which is the last multiple choice question, the electric field at a point is defined as. You know why you are given such a question? Because you confuse electric field with electric field at a point, right? This is electric field at a point, which is the force experienced per unit positive charge placed at what? Placed at that point. So the correct answer will be what? Will be A. So I think they were also supposed to include the option of the region in space, which is the electric field. Ne? So please, learners, let's not confuse the two. which is your electric field, and your electric field at what? At the point. Right, so now let's look at the structured questions on electric field at a point. Calculate the electric field strength, which is the electric field at a point, as 30 centimeters from a 5 Newton Coulomb charge. So now, there are two equations that you can use to calculate electric field at a point. E equals to F over Q, E equals to KQ over R squared. Okay, so which one to use here since we're given the distance? Obvious, it should be what? E equals to what? KQ over what? Over R squared. Okay, so calculate the electric field at a point 30 centimeters from 5 Newton Coulomb charge. All right, so the distance is 30 centimeters. Obviously, we need to convert that to meters, divide by 100, which is going to be 0.3 meters. The charge is in nanocoulombs. Obviously, we need to convert that, which is equals to 5 times 10 to the power negative 9 what? 9 coulombs. Okay, then let's calculate. We have E equals to K, Q over what? Over R squared. What is okay? 9 times 10 to the power 9 times Q, which is 5 times 10 to the power what? Negative 9 over R squared. What is our R? Is 0.3, but it should be 0.3 what? Squared. Then you get your answer in what? In newtons per coulomb. And remember, learners here, we did mention this when we were dealing with a Coulomb's law. Your charge here, this charge, should always be positive. It should be the magnitude, right? So even if it's negative, right? So here you need to substitute by what? By a positive what? By a positive charge of that magnitude. Okay. Then what are we having here? I'm having 9 times 10 to the power what? To the power 9. Multiply that. So it's 9 times 10 to the power 9. Okay, multiply that by 5. Multiply that by 5 times 10 to the power negative 9. Okay, divide by 0.3 squared. So here I'm getting what? 500 Newton per what? Per coulomb, right? So 500 Newton per what? Per coulomb. So that is our electric field at a point. So these are some of the questions that you will get. Okay. Then the second one. So you can see now I'm having more than two charges. Okay. I'm having a positive 3 and what? And a negative what? And a negative 4. Right? If they can ask you between the positive 3 and the negative 4, which charge has excess electrons, or which sphere has excess electrons, obviously you must be able to tell them that a negatively charged sphere has excess of electrons, right? Because remember, if a sphere is negative, it means that it has more electrons than what? Than protons. Okay. Then let's look at this one. Two charges Q1, which is plus 3 nanocoulombs, and Q2, which is negative 4 nanocoulombs, are separated by a distance 40 centimeters apart. So obviously we need to convert here. This one will be 3 times 10 to the power negative 9 coulombs. This one will be negative 4 times 10 to the power negative what? 9 what? Coulombs. This one will be 0.3 meters. This one will be 0.1 what? Meters. Converting from centimeters to meters, I have to divide by what? By 100, right? So this is what I have. So here, what are they looking for? What is the net electric field? So now they talk of the net electric field. Ne? So what is the net electric field at a point that is 10 centimeters from Q1 and 30 centimeters from what? From Q2. So they're talking about a point here, right? So we should know that a point, right, is always what here is always positive, unless if you are told that that point is negative. But if they just say it's a point, you should know that the point is always what? It's always positive. All right. So this is a positive one, a positive point. then first thing that we need to do here, maybe before we deal with this one, we can even go back to this one. We can even do what I want to talk about even here, right? So if you have a point here, you have a point at there is point X here. So this point X is what? Is positive, right? So if you want to determine the direction of the electric field at a point, right, you can use your vector diagram. I can't say it's a free body diagram because a free body diagram is a diagram of forces. And here we don't talk of forces. We are talking about what the electric field, which is a vector. Hence, I'm saying it's a vector diagram. But I'm going to draw it as a free body diagram. All right, but I can't say it's a free body diagram. It should be a vector diagram, right? So this point represents X, right? Then this is positive. Even your X, which is a point, is also what? Is also positive. So this X, the force exerted by what? By positive 5 newtons nanocoulombs to X would be the force of what? Of repulsion. Okay? So it is going to be the force of what? Of repulsion. So will this point X move towards or away from this positive 5 nanocoulombs? Obviously, it will move what? It will move away. Already here, you have the electric field experienced by X due to what? Due to positive 5 nanocoulombs. So this is the direction of the electric field experienced by what? By X due to what? Due to the positive 5 nanocoulombs. So if here they wanted the direction, then the direction was going to be toward to the right here. If we are using the relative directions, né? So it was going to be to the right. So what I'm encouraging here, learners, is to start by drawing a vector diagram. Okay? Draw a vector diagram. In that way, you'll be able to give the direction of the electric field at a point. Okay? So the electric field exerted by what? By positive 5 nanocoulombs to X. Obvious, the direction will be toward to the right. Né? So let's check this side. Right. So first thing that you need to do is to draw the vector diagram. So this is point X, right? So will point X move towards or away from positive 3? Obviously, it's going to be away. So this is the electric field exerted by what? Positive 3 nanocoulombs on what? On point X. Then again, let's draw the vector diagram. The electric field now exerted by what? By -4 to point X. Then obvious there is force of what here? Of attraction. So actually point X will move towards -4. Because remember point X is positive, right? So there is force of attraction. So point X will move towards what? -4. So it's towards. So this is the electric field exerted by what? -4 nanocoulombs on which point? On point X. So this is where we have to start. This is where you have to start. So the point is always what? Positive. Simple, just ask yourself a question. Whether this point X will move towards or away from -4. Obviously, it will move towards to that negative what? -4. Already, you have the direction of the electric field exerted by what? -4 nanocoulombs to point X. Then ask yourself a question again. Will this point X move towards or away from this positive 3 nanocoulombs? It will move away. So obvious, this is what you are going to have, right? So this is where we have to start. Okay, then from there, what are we supposed to do? calculate now the electric field exerted by what? By positive 3 nanocoulombs to point X, right? Then it's going to be 9 times 10 to the power what? To the power 9 times charge on what? On positive 3. Obviously, it's going to be what? 3 times 10 to the power negative 9. What is the distance between 3 and point X? Is 10 centimeters, which is 0.1 squared. Ne? Then you'll get your answer there. Then the electric field exerted by what? By the negative 4 nanocoulombs on what? On X. So it's K Q over R squared, which is 9 times 10 to the power 9. What is the charge? Is 4, not negative, remember, times 10 to the power negative what? Negative 9. What is the distance? Remember the distance they said is 30 centimeters, which is 0.3 what? 0.3 squared, right? Then let's calculate. We have 9 times 10 to the power 9, right? Multiply that by what? 3 times 10 to the power what? To the power negative 9. Okay? Divide that by what? 0.1 squared. So here I'm having 2,700 what? Newtons per coulomb. In which direction? To the right. Okay? Then 9 multiplied by 10 to the power 9 times 4 times 10 to the power negative 9. Okay? Divide that by 0.3 squared. So I'm having 400 here. Newtons per coulomb, again also to the right. Then we confirm the first one. I'm having 9 times 10 to the power 9. Multiply that by 3 times 10 to the power negative 9. Okay? Yes, so it's correct. Yeah. Right. So this is what I have. Then the net. So you can see both of these vectors, they are acting along a straight line and they're acting in the same what? Direction. So I'm taking this direction as what? As positive. Why am I choosing direction? Remember, electric field, it's a what? It's a vector. Ne? So E net will be what? E exerted by positive 3 nanocoulombs on what? On X, plus E exerted by negative 4 nanocoulombs on what? On X. So fortunately, they're acting in the same direction. So we are taking that direction as what? As positive. So what is E and 3 nanocoulombs on X? Is 2,700 plus 400. Then your answer, so it's 2,700 plus what? Plus 400, which is going to be what? 3,100 what? Newtons per coulomb. Obviously in the same what? In the same direction. So these are some of the things that you need to be able to do when we are dealing with what? With electric field at what? At a point. Calculating the net. Calculating the net. Okay. So net, remember we've only focused on charges along a straight line when it comes to electric field. So you shouldn't have a problem. So there's no way there where we are going to use the Pythagoras theorem because they're not at right angles, those charges. So you only focus on those charges along what? A straight line. First thing that we need to do is to draw a vector diagram exerted on that what? On that point. And that point you should know is always what? Positive. If it's not positive, they will mention that it is no longer positive for this scenario, it's negative, and you need to deal with that. For example, what they can say, for example, at point X, they've placed an electron. So what are they trying to say to you is that this point X is no longer positive, but is what? Is negative, because the electron is what? Is negative. But if it's that is not mentioned, you should know that the point is always what? Positive. That is very, very important, learners. Okay. Then here we have two identical spheres P and T, which are placed 0.1 meters apart, as shown in the diagram below. Then P carries a charge of 3 times 10 to the power negative 6 coulombs, and then T carries a charge of negative 3 times 10 to the power negative 6 coulombs. What is nice about this question? No conversion. Ne? So the charge is in coulombs, the distance is in what? Is in meters. Okay, so this one is clear, right? So first thing that they want us to do is to state Coulomb's law in weights, which is what we can do. Then draw the resultant electric field pattern due to the charges on P and what? And T. So you have P, which is positively charged. You have T, which is negatively charged. So don't change the way they are placed, right? So you can see they are placed vertically. So you're not expecting you to draw them horizontally. So draw your electric field pattern the way it is, or the way these charges are placed. Okay? So don't change the position. Don't change the position, because if you do that, we are going to penalize you. So they're not placed horizontal in this case, but they're placed vertically. So I'm drawing the electric field pattern with P, which is what? Positive, and then it's T, which is what? Which is negative. So obviously here there will be force of what? Of attraction. So I'm drawing that force of attraction. Make sure that the lines do not cross or touch each other. Then place a positive test charge. Then the direction will be from positive to what? Negative. Positive to what? To negative. Right. So to negative from positive. Then we'll get all the marks. Okay. Please, we don't change the position of what? Of the charges. Then a third charge sphere S of the unknown charge QS is placed at a distance of 0.5 or 15 meters from the sphere T, such that the 3 charge spheres are at vertices of a right angled triangle. The net electrostatic force on sphere T due to other 2 charge spheres has a magnitude of 10 newtons, as shown in the diagram below. So here, learners, please again, let's not confuse the net electric field with the net electrostatic force, right? The net electric field with the net electrostatic force. So because in most cases, learners, they confuse the two. Learners are asked to calculate the net electric field, they calculate the net electrostatic force. They are asked to calculate the net electrostatic force, they calculate what? The net electric field. So please be careful. Net electric field, obvious, is electric field E equals to KQ over R squared. Net electrostatic force F equals to KQ1Q2 over what? Over R squared. Okay, so this is how they are placed. And then here there's a question, is charge Q positive or negative, right? So here you have the net, right? So you have P, T, and S, right? And then this is the net electric field. Let's go back. The net electrostatic force, on sphere T due to the other 2 charge spheres. So the net electrostatic force is due to T. It's on T actually. On T. So T is negative. Okay? If T is negative, let me draw a free body diagram. I can say it's a free body diagram because now I'm dealing with forces. So T, it's what is negative, right? But remember your P is what is positive, right? So between P and T, there's force of attraction. So obvious, T will move towards. I'm drawing the free body diagram on T due to P and S. So the dot here should represent what? Should represent what? T. Okay? So T will move towards P. There's force of attraction. Now, check something. I'm giving what? The direction of what? The direction of the resultant or the net electrostatic force. Okay? Let's say remember, charge Q is either positive or negative. Let's say your Q was negative, S was negative, right? And your T is also negative. So you can see there's force of repulsion. Then obvious T was going to move to that direction. Then your net was going to be like this. So which means that your QS can never be negative. It should be what? Positive. Because between positive and negative, there's force of what? Of attraction. So it will move what? Towards. Then I will have my what here? My net. Okay. So for you to be able to do this, you must understand what you did earlier this year when we were dealing with what? With vectors in 2D. Okay? Vectors in 2D. Okay. So it means that my what? My Q is going to be what? Is going to be what? Is going to be positive. Okay. Then calculate the number of electrons added or moved from sphere S to give it a charge of what? Of Q. So here they are looking for what? The number of electrons added to what? Added or removed from sphere S to give it a charge of what? Of QS, ne? Yeah. So here you can see so it's what? It's positive. So first thing that you need to do here, you have to calculate. All right. You have to calculate what? The charge on S. Then after calculating the charge on S, then you can calculate the number of electrons that were removed or added. Okay. How to calculate the charge on S? First thing, you have your free body diagram, right? So this is what we have, right? 10 newtons here, your net. Here you have your force exerted by what? By P on what? On T. Here we'll have force exerted by S on what? On T. This is what we have. Ne? Right. So your net, because they are at a right angle triangle, your net here, your net force will be equals to the square root of Fp on what? On T squared plus Fs on what? On T what? On T squared, which is the same as this, your Pythagoras what? Theorem. If you still remember how to calculate the resultant for vectors in 2D, okay, or forces in 2D. Then from here, remember, what are you looking for? You can start by calculating a force, but it's going to take time. What they've done here, they've calculated what? The charge. Okay? So this is FTP, right? So FTP 9 times 10 to the power 9. Then Q1 is 3 times 10 to the power negative 6, which is your P. And then your T, it's what? It's negative 3 though. But remember here, you substitute by what? By positive. Divide by 0.1, which is the distance here, right? Then Ft on S, 9 times 10 to the power negative 9. And then what about your T? Is 3 times 10 to the power negative 6. Then you are looking for what? Looking for your Q2, okay? Then what is the distance between T and what? And S? It's what we are given is 0.15. Obviously, it's going to be 0.15 what? 15 squared. What is net on T? Is 10, but here they said is what? Is 10 squared. So if I did this, it means that I would say 10 here, but here is the square root of everything, which is what is going to be, it is going to give us the same thing, all right? Then calculate, then you get your what? Your QS. Then the charge on S, remember, is positive, ne? So what is the magnitude of that charge? Is 4.887 times 10 to the power negative 6 coulombs. Why they didn't round off this? Remember, it's not the final answer. You should do the same. You only round off your final answers. Then the equation is Q equals to NE. Then this is the charge, right? Then you'll be able to get what? To get the number of what? Of electrons. So these are some of the questions that you'll get. But because of time, I think we'll continue next time with a electric field. But I think you have seen how we do or we deal with questions under what? under electric what? Electric field. So thank you so much, learners, for attending this lesson. I hope you have gained something, and keep on asking questions. We'll assist you. If there's something that you didn't understand, your teachers are there also to assist you. So thank you so much. See you next time. Bye-bye.